You asked for detail. We tried to, they were doing maybe coming from that tomorrow.
Okay, if possible.
Yeah.
If not.
All right, folks. Can you hear me okay? Yeah. Okay. Let's get this started. Good afternoon. Welcome to this week's colloquium. It is a real pleasure for me to be able to introduce Professor Daniel Apai. Professor Apai earned his PhD in astrophysics from the Heidelberg University. And perhaps to the surprise of some of you, he was actually a staff astronomer here at the Space Telescope Science Institute from 2008 to 2011. After which, he joined the University of Arizona faculty in 2011. He's now a professor of astronomy, planetary sciences, and optical sciences, and served as of 3 weeks ago as the Associate Dean for Research in the College of Science. His work spans exoplanets and astrobiology, from the formation and habitability of planetary systems to the characterization of exoplanets and brown dwarf atmospheres. He also leads the NASA-funded project Alien Earth. Professor Apai's contribution have been recognized by his selection as a Fellow of the American Association for the Advancement of Science and as a member of the Explorers Club. Most recently, he has been spearheading an ambitious mission concept for a space telescope constellation, which is actually the focus of today's talk, entitled 1,000 Earths, Progress Towards a Constellation of Very Large Space Telescopes for Statistical Biosignature Surveys in Extrasolar Planets. Please join me in welcoming Professor Daniel Apai. Take it away.
Thank you. Thank you. Thank you. As Nestor mentioned, I was working here 15 years ago. Hard to believe by now. It was a wonderful place, and it's so nice to see so many familiar faces. It's always nice to come back. Today I want to tell you about a project Nautilus. This is a space observatory concept, and even more important than the concept is the technology development that's underpinning it. And the goal is captured pretty much in the title itself, 1,000 Earths. So we are as the title tells you, we are really aiming to find a way to reach a large number of planets to enable statistical comparisons of small, potentially Earth-like planets. So this is a work that is mostly led at the University of Arizona, and I wanted to point out key contributions from Tom Milster and Daewoo Kim, my colleagues in the College of Optical Sciences, but with also important contributions from outside the University of Arizona. Okay, let's jump in. So I will start by showing you the animation, a vision of what we are trying to build, which will look a bit strange. Some of you may find it disturbing. But then I will explain over the course of the next slides why it looks different, what's the goal, why it actually makes sense. Okay, so let's start with this. It starts with the rocket, and it could be a Starship, it could be another large rocket. One of the key things we want to do is use these large rockets, this is an astronaut for scale, to launch a space observatory. But the space observatory would be different from how we work today, because it would consist of not one, but many units. These would be many identical units that we would launch. And they look different, but I will explain to you why the difference makes sense. These ones, the astronaut there was for scale, but these ones in this rendering, the goal is to have 8.5 meter apertures with which we collect light. You will notice that the optics looks very different, and I will explain why. Each of these units is launched in a compact configuration, and upon reaching orbit, they would be deployed, putting the front optics in front of the unit. All of these are identical telescopes. They are not formation flying, so there's no interferometry here. The relative positions really don't matter. This is an incoherent array. They could be dispersed in any ways. The key advantage here, of course, is that you build a much larger light collecting area by launching multiple units. Okay. So this is one launch. We envision currently 2 rocket launches. Also, if you go with a different rocket, depending on the pairing, you may end up with a larger number of launches, depending on what you're collecting, light collecting areas. These observatory would be capable of not observing just one target, but it could observe many targets at the same time. So unlike for Hubble or James Webb, you don't have to decide where you are looking at, but the community could use these units parallel. If you do need the combined light collecting power, you could turn these units to observe the same star or the same planetary transit at the same time. So with sufficient units, we are targeting light collecting power that is equivalent to that of a 50-meter space telescope, 50 meters. So this all looks very strange and maybe unusual, but I will show you why it makes sense. I will also mention that this is not just a PowerPoint project. We are actually modifying buildings at the University of Arizona, and we are primarily worried about currently whether the city of Tucson can provide enough power to fuel some of the machines that we are using. So we got actually pretty far in this project. But let me start with the motivation. Our goal is the search for life in the universe, but really more scientifically, we want to understand the diversity of Earth-like planets, and then understand the processes that shape them, and look for those where we have to invoke life to shape the planet to explain the observations. This is a goal that has been broadly, of course, recognized throughout all the strategic reports over the past 15, 20 years. It has been ranked, as you know, as top science driver for the next decades, both by the Astronomy Decadal Survey and also by Planetary Science and Astrobiology Decadal Survey. So the Astro 2020 makes a recommendation that for this science case, we, of course, should go ahead and build a 6.5 meter diameter direct imaging mission. The approximate cost for this could be about $10–11 billion. There's no real firm cost estimate, but that's, I think, what most people think would cost. It's a very exciting concept, and it would have the benefits of building on James Webb and HST-derived technologies that would combine, when combined with high stability and coronagraphy capabilities, would allow studying about 25 habitable zone planets. The exact yield will depend on the configuration, will depend on the performance, will also depend on the actual occurrence rates of habitable zone Earth-sized planets. The number currently used is maybe 25%, but of course the real number may be quite a bit lower. So I think higher is very unlikely at this point, but yes, we can talk about that if needed. Complexity and diversity of exors. So some of the questions, of course, that we have to think about is if we observe these planets, will we be able to interpret the signal, what we are seeing? So I think there are many arguments made in the literature that point out that if we find exactly Earth-like planets, we have a good basis for interpreting it. But should we expect that all of these planets will be very similar to Earth, or maybe they will look different? So there are white papers, there's one white paper I wrote there. Others have wrote other reports and white papers arguing about the likely complexity of worlds that maybe Earth size, maybe in a habitable world, habitable zone, but it doesn't mean they are necessarily Earth-like. So there are parameters that we are directly able to probe, like mass, radius, present-day irradiation, but there are also other parameters of planets that are inaccessible to direct observation. And you can see a couple of them listed here. Mostly they are basically beneath the atmosphere, beneath the interior, or in the past, so we cannot directly probe them. So this is a plot from Vicky Meadows' group showing the likely complexity. These are basically, if you just think about Earth, right, it's a fairly complex planet. Mars, of which we know much more about than any exoplanet, it still remains difficult to interpret. The way I like to think about it is basically an n-dimensional parameter space. The key parameters of the planets could be different dimensions, and every planet I observe could fall basically in this n-dimensional parameter space, maybe sampling the sizes, the atmospheric composition, irradiation, etc. So one question is, what is the dimensionality of the parameter space in which we'll be placing these planets? If it's a low-dimensional parameter space, or there are processes that force the planets to all look the same, there's a convergent evolution in the planet sense, then a smaller sample size will suffice. If the complexity is greater, then you need a larger parameter space. So I think a 10 or 10 plus dimensional parameter space, in my opinion, is a fairly safe bet when we talk about the complexity of Earth-like planets. Okay, so I think there is a challenge, obviously, here. One challenge is that with direct imaging is really the best way forward if you can build one telescope only, and the telescope will be used to probe nearby planets. The most efficient way to sample those planets, to study those planets, regardless of their inclination, is to do direct imaging to spatially separate light from the planet, the star from the planet. And this works very well for nearby stars. It works less well to build up a large sample. It doesn't work that well for large samples because you have a diffraction limit, you have a finite limit, resolution limit of your telescope that is given by the telescope's design. In the simplest case, is the diffraction limit or a factor of a few larger. And you have to match that spatial resolution your telescope delivers to the critical spatial scale in your system, which is the habitable zone separation. So with a given size of the telescope, you can only probe that far in space to resolve the habitable zone, and that means that you only can detect planets in that volume. So if you fold in the occurrence rates of Earth-sized planets in the habitable zone, that we now have better and better constraints, and you can also fold in the fact that telescope costs are sharply increasing with diameter, then you are basically, if you follow these arguments through, what you will find is that it's a cost-effective way, direct imaging is a cost-effective way for nearby planets, but not for faraway planets. And that means also that it's very difficult to build up a large sample. Okay, so, and I think most of you know this, so there's probably nothing new in here. Let me introduce 6 numbers here. And 6 numbers that I know many people are kind of worried about. One is that it takes now about 30 years between astrophysics large flagships. It depends a little bit how you define flagships, etc., but we are really talking about multi-decade-long projects when we embark on any of the big ones. So that is obviously, I think the community does amazing work in certainly with HST and then James Webb, with realizing some of the most complex, most ambitious space missions ever flown. And I think that's all well recognized. And these timelines are also in part driven by the funding that's available. So it's more difficult to make them shorter, but I will address this a little bit. still, this is a problem, and the people who work on the mission may never get to use them, right? How do you actually transfer knowledge from building the observatory to using it if you have a generational change in between? Also, how can we make sure that 30 years from now, our telescopes or instruments will be addressing the right questions when we are building them now, and science is changing on a much faster timescale? The other problem is that we are looking forward to 2050, right? 2045, 2050, and the current technology, we are not envisioning the current technology to increase much in size. So that kind of suggests you that this is a technology that is close to plateauing. In fact, we have not been really building much bigger mirrors as single monolithic mirrors in the past decades. There are other concerns, right? James Webb is an incredible, I think, testament to the ingenuity of everybody who worked on, especially the engineering teams. They managed to control 170 single point failures, and not one of them came to be. So that's amazing, because if any one of them would have become materialized as a failure, we would look at a very different future for astrophysics. It is really an amazing, again, testament to everybody involved that this mission is going so amazingly. But at the same time, it is still a risk, right? We pack a lot of risk, we concentrate a lot of risk, funding, time, and effort into a single unit. And I used to think that we know how to build James Webb, we know how to build Hubble. If this would, if this would have failed, we just know what to fix, we could build another one. But that's not the case. Most of the people who actually were involved in the initial phase of James Webb no longer working actively on the project. Many of the vendors that provided pieces, they would not be able to just go back, restart the computer, and create the same versions again. So we really are not in a position to easily replicate James Webb. And that is not just James Webb. It's basically the current model in which we are working is basically concentrating a lot of time, a lot of risk into a single unit. At the same time, there is and I think that's a technological challenge. At the same time, we have a scientific challenge. This is kind of what I mentioned. When talking about Earth-like planets, I think we really have to think about the complexity that we are going to find there and make sure that the data we acquire will be suitable enough to tackle that complexity. So I think about this as basically sampling a 10-dimensional parameter space. Now, if you want to understand patterns, trends, outliers, processes that shape a distribution of points in a 10-dimensional parameter space, what you need is data, right? But I don't know exactly how many points we need to sample a 10-dimensional parameter space, but we need a larger number. But because of the nature of direct imaging, that's effective for nearby systems, and those are very important. They have high information content too, but that's not a technique that is going to deliver a very large number of planets. So we have, as a way I look at it, we have a technological challenge, and then we have a scientific challenge. This is in the field of exoplanets, but some of these actually translates to other fields too. Those are challenges, but we have great opportunities, and actually that help us to solve some of these challenges. One of these opportunities is the complete reformation of the launch industry. So I'm sure everybody is aware of the changes that happen, but maybe not everybody knows the extent to which they have been reshaping opportunities. So this is one example of a reusable rocket. Many others have been launched. SpaceX is most known for bringing in this transformation, but it's not the only one. In fact, there's now a whole slew of companies following that, their example. Starship, which is in the works and hasn't been completely successful yet, but they are getting pretty close to it, is the largest rocket ever launched, largest volume. It will bring up the greatest mass to orbit at the lowest cost. And not only that, but it is designed for high cadence flights. So whether or not they reach it, but their goal is to be able to launch this every few days. Okay? So this is very significant. It's not a Starship, of course. There were much bigger changes in the space launch industry in general. So let me highlight this. So if you go back to like 1960s, and from 1960s to about 2010, getting a kilogram mass into orbit costed you somewhere between $10,000 to $50,000, depending on the complexity of mission, whether a crew was involved or not. But then you start to see a rapid drop of in launch cost. So that is not just incremental change. This is basically this is a log plot. This is an order of magnitude and more reduction. Now, much of this is due to SpaceX's Falcon 9, but again, they are not the only one. There are now multiple other companies in the US and multiple companies in China. There are 3 of them in China that are very close to catching up. Let me show you this graph. So this is a number of objects, mostly satellites, launched into space. You see here basically the rapid transition, where we move from a relatively steady use of space to basically an explosion in the number of units launched. So that's very significant, and this doesn't even include 2025. In 2025, Falcon has flown over 100 times. So that basically completes more than 500 flights for the Falcon 9. Other countries are catching up, and of course, we all hear about mega constellations where people are considering and actually building and deploying constellations with thousands or even tens of thousands of satellites. Okay? This is a complete change in mentality, in mode of operation from what has been the norm for 60 years, for much of the space age. Okay, so are we fully taking advantage of this? This article from 2023, I think 2022, science article, I was not involved, a number of experts were interviewed, and they all said that no, the reality is that space scientists are not really taking advantage or thinking forward on how this reshaped launch industry will enable science. So this was an interesting read. There was another paper, some of you may have seen this before. This is from Dan Goldin, who was the longest serving NASA administrator, serving under 3 presidents. And Dan has a well-informed and strong opinion about arguing that we need to look at much bolder visions of the future than what we are working on currently. So then I connected with them because he pointed to our mission as one example that NASA should be considering. So I thought, he's right, we should chat. So what I'm seeing basically is that we have a current telescope technology that is just not scalable, right? If we are building a same size telescope 25, 30 years later, it's hard to argue that it's a scalable technology. At the same time, we have grand challenges in astronomy and planetary sciences that require much more capable telescopes. In some ways, we are building those. In other ways, we are not. At the same time, we also have a technological revolution in launch vehicles. That's a fundamental game changer. But these arrows don't meet. What I think we need to do, and that's what we have been working on, is rethinking space telescopes, creating scalable optical solutions, and systems that benefit from the economy of scale so that we can benefit from these opportunities to address these challenges. So let me take you back a little bit and briefly address this question. And in all of these slides, I could go deeper, but I'm just trying to stay a little bit on the surface and happy to take questions later. So how could we probe 1,000 exo-Earths? This basically, and this brings me to the Nautilus science goals. I started this project now 8 years ago. Basically, just along these lines, I could foresee where the reusable launch vehicles are heading, where the launch costs are heading, where the challenges that we are facing emerging, and I thought, let's try to see if there is another way to solve these problems. So our science goals are fairly unsurprising. We would like to determine the diversity of Earth-sized planets and search for life via atmospheric biosignatures. I think the key difference is that we believe that we need a large sample. This has to be a statistical study. And that means that we need to be able to sample a large number of planets. But we, of course, want to be realistic, so we don't want to create a mission that is unrealistically expensive. So could we do this? So one of the first things we done, of course, while I love direct imaging, and many of you know that I have worked a lot on direct imaging and still have projects there too, if it's about large sample sizes, if it's about large sample sizes, transits will have an advantage. And that is because in transits, to observe this is of course an artist's impression, we don't actually see the planets moving in front of the stars, but we don't have to because we are looking at the temporal modulation. And that means that this is much less sensitive to distances. Think about that. Kepler, which is a pretty small telescope, could detect Earth-sized transiting planets more than a kiloparsec away, okay? Easily about 100 times farther than what you can do with direct imaging, even with the largest ground-based telescopes. So it's much less sensitive to distances. You still need large telescopes, and I will get to that, but it is less sensitive to distances, so you can probe a much larger volume. So in a paper in 2019, we went through the numbers and simulated that if you wanted to study the closest 1,000 transiting planets around M dwarfs, or the closest 1,000 transiting planet at all, regardless of the host stars, or you wanted a 50% M dwarf, 50% FGK star sample, or only sun-like stars, how far in space would you need to be able to detect and characterize those planets? And so it brings you around, there are many more M dwarfs, so M dwarfs are relatively nearby, so you could build up a sample from relatively close systems, or if you wanted to study sun-like stars and Earth pairs, then you would need to go further. You can find the details there, but this is basically what informs. Okay, I think I ran out of battery. Or not. Okay, something. This basically informed simulations for the sensitivity that we need to reach. And so these are simulations. We have others too. We used, in this case, Earth as a template to assess how far, how would the signal to noise look if you observe transits. You would be able to detect water, oxygen, ozone, if you have right stability, sufficient stability, and also photon noise, low enough photon noise. So it turns out that actually Kepler already reached a photometric stability that is very similar to what is necessary. So in that, you wouldn't really need to push the stability much more, maybe a factor of a few. Where the biggest assumption here in this simulation is the light collecting power. So to get this kind of spectra, to be able to study Earth's analogs at 300 parsecs, you need a huge telescope, a 50-meter telescope. Of course, that's all ridiculous, right? We cannot build a 50-meter telescope, but I will show you how we can still collect the photons. Okay, so it's a good idea to actually ask yourself this very basic question: why can't we build a 50-meter telescope? And on one hand, this looks ridiculous. Of course, we cannot build. But on the other hand, if you see how much progress we have made in technology, in many other parts of life, from computing is of course a great example. It is not an unreasonable question why we cannot just build a 10 times larger device in 30 years. So this goes to the space spiral. How many of you know about the space spiral? Okay, Nestor already heard my talk, so it doesn't. Okay, so the space spiral is basically goes like this. It's not from me. It's basically, you can find it in textbooks. It's expensive to go to space, so missions are expensive to start with. Now, if they are expensive, we cannot build many of them, and so if we can build only one infrared telescope, one UV telescope, one X-ray telescope, then they all end up being unique telescopes, and we want them to do everything because we only get one infrared telescope every 3 decades. So we end up in this spiral with complex missions with no tolerance for failure. It has to work because we only have one. And if it has to work, and we cannot take any risks at all, then it will be expensive. So you are in a spiral, and that spiral just increases. Now, if your budget is capped, as the environment in which you work, the only way this spiral can expand is in time. So that's why missions take longer and longer and longer to complete. Okay, we are not the only one. This was basically the mode in which everybody else operated. But they no longer do that. Why? Because the entry point to the spiral doesn't exist anymore. It's no longer expensive to go to space. It went from tens of thousands of kilograms to a few $100. So tens of $1,000s per kilogram to $100 to $200 per kilogram. It's not any more expensive to go to space. It's the rest of it that can be expensive. Now, it changes the economy, right? What happens is similar, and it is true that the majority of the cost of a space mission is not the launch. But if the launch is expensive, it doesn't make sense to save on the rest, right? It's very similar to if you are a real estate developer and you develop buildings in Manhattan, right? You will always end up with skyscrapers, high rises, That's the only thing that makes sense because land is expensive. But imagine that you are now a real estate developer, you moved into the suburbs. Are you going to build high rises? No, what you will build, many units that are similar, you share, basically, you create these mass producible units. And that will give you a better investment. That's pretty much what's happening in many other uses of space, apart from space sciences. So communication is transitioned from massive, very expensive telecommunication satellites to highly resilient, mass-produced units. I think everybody's familiar with Starlink. They are the greatest example, but not the only one. Now, many, many users are not launching telescopes by one, or satellites generally, by a single unit, but they are launching them by the dozens. That's basically how orders are made. So those who are able to deliver systems at low cost rapidly that are scalable will be able to make use of this change. So again, why can't we build a 50-meter space telescope if launch costs drop by 10x? The problem is we are still, of course, if we just build one, we are not benefiting from the economy of scale. We cannot fit it in a rocket, of course. But basically, the technologies that we developed onto this point in the spiral, in the way we work, they are inherently expensive. And many of them are tied actually to optical systems that don't scale well. So we are just, in January, maybe in December, we are launching the Pandora smallsat. That's just a bit of a segue, led by the Goddard Space Flight Center. That's a 0.5 meter space telescope, a smallsat that will do transit spectroscopy, and the budget is $20 million. And it's actually not the first in that series. There were already other similar units launched. And basically, my point is that this is really a small cost for a space telescope developed quickly, and it's actually mass producible. Everything on that could be produced, replicated multiple times, maybe except for the optical system. But basically, when we started this project, we converged on this. Large mirror-based systems are expensive to fabricate. They take a long time to test, integrate, and then operate. They are just expensive. There is a reason, if I look around, I see many eyeglasses. Nobody is here with a mirror-assisted eyeglass system. And that's because transmissive optics are much easier to work with, okay? In every day, we basically never use mirror-based systems. Your cell phones, your cameras, your camcorders, they don't use mirrors. We use mirrors because we cannot scale lenses. That's basically what we solved here. So the challenge of, and maybe I will just go a bit quicker here. There's so many interesting things. I'm happy to tell you more about this. This is kind of the history of the evolution of telescopes, and I'm sorry for the Italians. I left Galileo here off. Just didn't fit in the logarithmic plot. But basically, I think the two key points that I want to take away here, is that it is not a continuous progression. Like with any technology, there are parts when we are segments in time when we are able to make progress, and then a technology plateaus. And in these plateau technologies, like refractors up to about 1 meter, we were able to make progress. But we reached a point where it just didn't scale anymore. It didn't make sense to do them. Also with reflective telescopes, we had different types, different modes of operation, how we made telescopes. Once the technology plateaued, you could spend much more money, but not get out much more in terms of gain. In each of these plateaued phases, we were eventually able to find a better technology that provided better capabilities at lower cost and often faster. And we see this in the ground, we see it in space, and we see it in other technologies too. So it's important to look for these changes. So there's a motivational quote to demonstrate I'm not the only one thinking about this, but we need to look for, and I think we are very good in space sciences in looking for ways to do things better and differently. But what we converge to is that we really cannot mass produce telescopes unless we can find a way to drive down the costs and create mass producible optical systems. Because I can mass produce instruments, I can mass produce the electronics, I can mass produce the spacecraft bus, but if I cannot do the optical system and everything else attached to it remains expensive and complicated, it won't work. So we started to create a project to replace primary mirrors. And every time did it happen to you that you think, oh, I have a great idea, and it turns out somebody 20 years earlier had the same idea. So it turns out that in the 1990s, and then in the early 2010s, 2 projects already tried to replace mirrors with diffractive optics. And my aim to build a 50-meter diameter accurate space telescope is ambitious, but these guys were aiming for a 100-meter diameter telescope. This is a 5-meter prototype, and they actually built the prototype, and the prototype was successful. What they do here is they use, anybody knows Fresnel lenses? Okay, so these are simple optical solutions where you basically have a pattern of transmissive or non-transmissive segments, and then basically you are able to focus light. They are, I will get a little bit more into details a bit later, but they are fairly simplistic. They worked quite well. With a 5-meter diameter, they were able to get diffraction-limited resolution, but there were 2 catches. So this was pretty successful. The other project was a follow-on project. The goal here, again, both of these were funded basically by DoD, DOE. The goal here is to launch quickly a 25-meter diameter telescope, position it where you need coverage for. They were not interested in exoplanets. And their goal was to look down, right? And this worked too. This is pretty amazing. This is membrane-based, so it's a lens that you can stretch and will give you diffraction-limited image quality if you stretch it well enough. And it's UV cured, so you actually can mass produce this. It's pretty amazing technology. There were 2 problems with both of these. One is that they really only worked in one single wavelength, monochromatic performance, which for these groups is probably okay, but we like more colors, so we want better performance. The other bigger problem is that the focal ratios were very long. So basically the focal lengths were so long that they imagined having 2 separate spacecrafts. So to my knowledge, these didn't advance further because of these practical considerations. But the idea has been there and it's been good. It turns out that in a commercial side, this idea is being used. So when I was even younger, when I went to a soccer match or tennis court, yeah, you could see on the field really long telephoto lenses. Like the journalists, sometimes 2 photo reporters were turning the lens. Those days are mostly gone. Photo reporters are using much shorter, more compact, lightweight lenses that provide higher image quality. How they do it is that the new lenses, they incorporate diffractive elements together with the conventional refractive lenses. Now this is good because a diffractive lens has the opposite sign of chromatic aberration from a refractive lens. So if you design it well, you can actually get a better image quality in fewer lens elements, and they can be much lighter. So this works. That's actually how the industry is nowadays working. So this is, if you want really sharp images from a cat, this is basically what you need to buy. So we wrote a paper in 2019 saying that, look, this technology could potentially enable mass production of large telescopes at lower cost. So we've heard out many of the initial questions for this, and I will show you some of that design, but much more about also the technology. So to make this happen, we had to solve the 2 problems that the DoD and DoD teams couldn't solve. That was basically broadband performance in a compact configuration. So I fortunately was able to connect with some of the best diffractive optics designers in the world, and so we worked with them to develop and patent what we call the MODE technology. This is the multi-order diffractive engineered lenses. Okay, what's the idea here? So imagine I have a conventional lens, right? A conventional lens focuses light because of the shape of the lens's body. So if I want to make this 10 times larger, I have to scale it in 3 dimensions. 10 times larger lens is 1,000 times heavier lens. So you can see that basically with the volume scaling, it's just not scalable. That's why we reach 1 meter, but we cannot build a 10-meter lens. What we do, however, is to basically create flat lenses. So we basically remove the plane parallel chunks from the lens, and that will give you a non-continuous surface. It's a bit blurred image. We lose some image quality there. But then that's already a flatter lens. And in the back, we can put a diffractive pattern there too. So this is a bit oversimplifying. But in essence, we end up with a lens, with a diffractive lens, another diffractive lens, and some refractive index left in the body of the lens. So I have a triplet now, an apochromatic lens that is nearly completely flat. In fact, because the focusing power of the lens comes from the diffraction pattern that we fabricate onto the surface, I can create much bigger diameter lenses without having to worry about the thickness. Okay, and this is in itself, it's a triplet apochromatic performance. So this is really exciting technology. It allows us to create lower weight systems than traditional mirrors. The weight saving compared to conventional mirrors is about a factor of 100. But even more important are the next two advantages. It's much less sensitive to misalignments. So if we want to operate these systems, just like with your eyeglasses, you really don't have to spend every morning 15 minutes aligning it. It's just going to be good when you put it on. So these are much less sensitive. And that's why we always use, as I mentioned, transmissive systems. The other one is a big advantage too. These systems are well suited for mass production. I will show you in a moment why. So these, when you combine these advantages, they translate to a great potential of cost reduction and faster timescales. So for those of you who love this, we patented it. These are some simulations. I will show you real images. These systems are not as good as a perfect mirror, but most of the mirrors are not actually perfect. But we can get diffraction-limited performance in a pretty broad wavelength range. We can actually push that if you want to. Our mission parameters were not requiring pushing it further. And we can also reach pretty wide field of views. This is not a limit, it's just our current design. Okay. So we first built, when we first said that this is the idea, we have the best experts in the world, we were told, no, you don't have the best experts, or experts saying that it's not possible. But we built a prototype, we showed them they are wrong. We published now more than 20 papers, high impact papers. We built a multiple generation of prototypes, so the idea is it's actually working pretty well. This was the first prototype still built in plastic. We could, on a standard Air Force target, demonstrate in the lab diffraction-limited resolution and also in the field diffraction-limited resolution. So we have patents on these. Other patents are pending. Some are approved in addition to these. The fundamentals are captured in this paper and also in follow-up papers. So the key thing here is not just that it works, but it can be fabricated quickly. So we use, and this is our old equipment, now we have much shinier one, I will show you briefly, but we can do this by optical molding. So this is something you couldn't do 20 years ago. For comparison, if you want to build a mirror, you are grinding and polishing. And so that's basically a global process. If I have an 8-meter mirror, and I made a mistake here, it's too deep, I have to repolish the whole thing, right? It's not something that you can locally fix. And because of that, we do some of the biggest mirrors in Arizona, 8.4-meter diameter in the mirror lab. Those are amazing, Rubin, GMT, Magellan, LBT, etc. But they take about 2 to 4 years to complete, right? And they are still heavy. So our goal here is to move this, basically move from years to much shorter timescales. The idea is to use the same kind of process that we are using for car windshields, which is basically temperature and pressure control and providing high quality optical surfaces. This is not possible because there was a whole significant set of breakthroughs in optical fabrication called freeform optics and optical molding. So we can reproduce with standard off-the-shelf equipment 3 to 4 nanometer precision with a single pressing in relatively large diameters, and we have passed for much larger diameters too. Okay, so these were some of the earlier prototypes, still pretty thick. And you can see the diffraction pattern. So, and then here it looks like it's scratched, like we dropped it, but we didn't drop it. Actually, this is the fine single wavelength diffraction pattern in the back. And so in the front, you can see the non-continuous surface, and put together, it works like a lens. We transitioned to thin glasses, and then we created larger molds. We have now, this was our first segment molded. We developed the technology to create segments and assemble from segments, so we can build bigger ones than we can fit in the machine. This was when we did, this was the largest precision molded diffractive optics in the world. This is how it looks. Now we have prettier ones, but this was the first one. If you illuminate in the right way, you can actually see the diffraction pattern. It's a little bit similar conceptually to, say, having a grating, and then you would create circular grating, so that would give you a focusing. The problem would be that the focus would be wavelength dependent. So that's basically where we do high performance computing optimization, and then process to create the mold so that we can suppress those chromatic aberrations. So we developed technology to align these segments and then integrate them together. So we are very happy when that worked. We have tested these on Sky, so these were integration tests. And the nice thing in Tucson is I could do this from my backyard with my students. You can actually see the lens here and basically how it just distorts the image of the cypress behind. So we have a setup also in the mountain just outside Tucson where we are operating the telescope. So we have on-sky observations. Okay, so that basically all showed, and we have more than 20 papers published. I will show you some of them, and happy to share the references if anybody's interested in that. But we basically showed that the 24 centimeter, we demonstrated a proof of concept. Then we now need to basically scale up in diameter and then also show that it works in space-like conditions. So we actually got a machine that costs like about as much as a Ferrari. And so when it was delivered, it's like 3 tons. And so they brought a forklift that was just a bit too short. So, and I was wondering, okay, is this, I mean, it just doesn't barely reach the half of the crate. Is it going to go through? And of course, it's super sensitive to shocks. So the guy told me, trust me, I do this all the time. I didn't trust him. But he was right, they got it in, so that was exciting. So now we have a pretty amazing machine. So this is a 170-meter cavity diameter molding machine. This is in a clean room. We have a new lab at the U of A where we can put the mold inserts on top and bottom, and then put in between a preform, glass preform. And then if this works, basically the machine closes, fills it up with gas, and then controls pressure and temperature, pressing the mold into the glass. So we have high performance supercomputer simulations of how the glass deforms, so we optimize the mold in that. The cool thing is that basically very quickly we can create these glasses, the high image quality. This molding takes now 50 minutes, and we didn't optimize for time. This is the first mold that came out from that machine. We are pretty happy with the quality. And okay, the next one, we have bigger plans, and we will need a bigger forklift. So the next plan, we have a proposal that is this close to final acceptance. It's a $4 million proposal. We were invited to submit it. It was reviewed 2 times, greenlit. We jumped through hoops. They came back 10 days ago, and they told us that the proposal was well reviewed, but you need to ask for more money because we like the project that much. So I thought, that's a problem we can solve. We did ask for a bit more money. We are very happy that, and so I'm told we are just waiting for final signatures. If we get the money, we will be buying a machine from Germany. This is a machine, we named it Oculus already, it may go into this building. We have another building we are considering. That's where the power and et cetera comes in. This machine can mold 1.7 meter diameter lenses, and it can do it in 4 hours. So it's basically no central obscuration. That's about the same light collecting power as Hubble has, roughly, and you could mass produce it. If you really wanted, maybe you could mass produce 2 a day. I would probably not push it, but at least 1 a day with this machine. So that's pretty exciting. We also have this segmentation technology. So if I don't want just a monolithic, but I actually want to use segments, with this machine we'll be able to go up with 1 ring segment, as you have seen, to 4.5 meters. Or if you had 2 segments, then we could approach 8 meters. So this will be, they already have, these machines exist. Nobody else is doing large diffractive optics. We are the only ones doing it, but they are used for other purposes. And this is something that it's very low risk. Okay, so how does this come together? So we have basically, for those of you like these scales, we are now basically TRL 4 and very on the way to approach 6. I will not show it here, but we have active thermal vacuum and vibrational tests in Arizona. We passed the first half of those phases. We are working towards launching a space demonstrator within 2 years at small diameters. And then with the machine I mentioned, we have a path towards really large diameters relatively quickly, 2 to 3 years until the machine and the lab are operational. Okay, so I will bring back this simulation. Okay, so I think many features in the simulation may make sense. So we are really looking at resilience through redundancy, many units. This distributes risks and costs unlike our current model. We look at basically making them pretty much identical, although some variations, we may decide to do some variations. Really the only innovative component here, why they look very different, but the only part that we need that doesn't have space heritage is the front optic. That's why we focus there. We have been pushing to develop that technology, and we are very excited about the progress. Again, this is not a formation flying. It's not an interferometer, so we don't have to worry about metrology or precision control or combining light. We would be basically, for transits, we would be observing transits, the same transit potentially with many or all the telescopes, and digitally record the signal. Just like Hubble or James Webb observe the same transiting system, maybe different transits, but the same system, and then digitally combines the signal. We can do the same, just with more telescopes, you can do it faster. Okay, it would have other advantages too. So we would be able to serve the community, a much greater community than you can do with one telescope, because you could use it for galaxy surveys, asteroids, solar system science, etc., doing all parallel, so it's more parallelizable. We also have the ability to distribute risks. So I wouldn't need to launch everything at the same time. I could launch up a Gen 1, learn from the Gen 1 mistakes, any potential issues, improve, and launch a Gen 2 or a Gen 3. This is basically what the current model is now for most users. I would say we don't have a complete end-to-end engineering design, so we are not at the maturity level that even the LUAR or HABEX teams were when they approached it. This is basically, we are focusing on technology development, concept development. We have funding and we are expanding on that, but it is not at the end-to-end level. Okay. I would say that so a single unit would have larger light collecting power than James Webb, Ariel, and HST. And of course, we want to build many of them. I argue in my paper also, and elsewhere too, that much of the discovery space actually in astrophysics, most of the discoveries came primarily from sensitivity gains and wavelength gains, and less from spatial resolution gains. So here we would be enhancing the sensitivity by a factor of 100 compared to James Webb. So just another comparison. So there is a lot of work that went into optical design, simulations, lab. So we had in the SPI in 2022, which was already a few years ago, we had a double session just covered in, basically just filled with talks on the optical design. In the optical science side, this really was very well received. So many of these were editor speaks, most downloaded papers in some of the top journals. So this is pretty well received. Our next goals are to scale up. So I mentioned already that we are very close to getting the funding to being able to place the order for the large diameter molding machine. We have funding from active grants, thermal vacuum tests, and then we are doing vibration tests. The sponsor that funds those tests is expressed intent to fund us to go to space relatively quickly, within about probably 1 or 2 years, to demonstrate in space that the system works. So that would bring us to TRL 7, 8, or 9, depending on how you define the system. We have a whole plan. We are working on a MIDEX concept, building on this technology. We have funding for the science technology, for the science case, science traceability matrix, developing preliminary instrument design. We have funding for the MIDEX concept. So I won't have time to go there, but you can ask me. We are not looking at taking one step from here to a flagship. We have a path through intermediate size missions that also enable new science and new uses in astrophysics, earth science, national security, and commercial missions. We have a financial plan how to get there. So this is just kind of a summary of some of the stuff we have done. Sky and Telescope declared us as the future of astronomy. I'm sure they're right. So we are really excited about the progress. This is basically, I will just end this the final slide. I really think that we are at a convergence point. We have new launch capabilities. There is a new optical technology, and we have new science questions. And you can bring them together, I think we are very well positioned. So we have developed a new optical technology to enable this. We are basically just, in a sense, learning from what other fields have done, transitioning into highly resilient systems that are produced by mass fabrication, launching constellations, distributing costs, weights, accelerating schedule for getting actual science out. And so for Nautilus, this is, of course, a flagship notion, a flagship concept within the cost cap of, I have many slides on cost estimates. That's a big thing, but I didn't include them in this talk, but I'm happy to take questions. We think that there is a good possibility, good potential for getting to 1,000 planets within an astrophysics flagship or a flagship cost cap. And with that, I think we could determine first the diversity of our size planets and then really search for signatures of life. Thank you.
All right, folks, questions. Let's start with these.
Yeah, thank you, Daniel. This is so cool. I mean, just so everybody knows, I saw this presentation a few years ago. Like, the whole thing has come such a long way.
Oh, yeah. Yes.
It's impressive. So I don't know if I missed it, but what is wavelength range that you're thinking about and the resolution?
Yes. So basically the wavelength range, there are two different things. One, in terms of what the wavelength. So the wavelength range in which the technology could work is very broad. It gets more difficult in the UV, but we could actually go pretty long in the infrared. For this mission, we are just from cost considerations, and we haven't really done trade studies yet, but from cost considerations and science, we are thinking on 0.35 to 1.78, basically, so just to avoid having to cool the system, longer wavelengths. But the optics could go actually longer wavelengths too. And resolution, we didn't do a trade study. We simulated basically with low resolution. What we did there as an initial starting point was taking the WIF-C3 IR basically as an example for an existing system, and then we based the simulations on that, but basically adjusting the telescope size. And maybe I would just mention very briefly the philosophy. So basically our goal is to show what is the simplest basically mission requirement that would satisfy the goals. And then once we have a engineering design, we can do trade studies, and we would want to see what else we could add up. So we would love to have higher resolution, maybe go longer wavelengths, maybe introduce differences between the telescopes. So some of them would have different field of views than others. But we first want to keep it the simplest design that's required.
So I'm super excited about this. This is all very cool. And I'm super excited about this highly replicated approach. And I feel like I've been hearing about it for 20 years now, that there's lots of great opportunities for doing things much more efficiently with this highly replicated approach. Virus comes to mind as an example in astronomy, but also LNSD technologies like the ATA. But it hasn't quite happened yet in astronomy. I mean, maybe I'm wrong and there's some massively replicated thing I'm not thinking of. But, of course, there's interferometers. We've had them forever. But those are combined. I'm wondering, do you see examples of that in the field so far? And if you don't, why not?
So I think that's a great question. I would say there are two answers to that. One is that if you look at Hubble is in many ways unique. In other ways, Hubble is not unique, right? It does derive from a program that had launched many similar telescopes, and you can find it on Wikipedia. So there wasn't as single as that was the only one for astronomy, but there were other examples. I would argue that until the launch costs were so high, it just really didn't make sense to replicate for us, for kind of the budgets we are working with. It really didn't make sense to replicate things. There is more to it because there's also politics on basically, aerospace companies, rightly so, they are probably excited about developing something one time. But astronomy and space sciences, we are not the one where they make the real profit. So they may be interested in developing new technologies, but We are not buying typically 100. So there's a little bit of how the markets work, what makes sense. But I think a lot of it is really driven by the fact that launch costs were very high. And compared to our budget, it's yes.
Thank you, Daniel. Super exciting. When I think about frontal optics in space, I think about star shades. Is there any technologies you can actually scrape from the star shade that could help you?
From the star shade, yes.
Yeah, I mean, NASA invested $50 to $100 million in star shade technologies, formation flying, all that stuff. Is there anything useful, or just
or sun shield?
Sorry?
Star shield or
star shade, the JPL star shade for.
So basically, I don't know, you saw Sarah Seeger is on it, and Sarah is really excited, and I share the excitement to use basically the initial units potentially with a star shade. So for a star shade, you don't, and in fact there are multiple advantages. First, for a star shade, you basically put the heavy lifting in the optical starlight suppression on the external occulter. So your telescope can be a simpler unit. So that there is a gain. If you can make a simpler unit at lower cost, that's good. But even better, basically the star shades, one of the key inefficiencies of a star shade is repositioning it, right? If you are pointing with an instrument that's 100,000 kilometers long, it takes a long time to turn around. But what if you had two telescopes, right? You could, while you are integrating with one, I could preposition the second telescope and then rotate the star shade, and so I would basically increase the star shade's efficiency by a factor of 2. Now, this only makes sense if the telescope is basically cheap enough that it doesn't add to the mission cost. But yeah, so I would say we are looking at it. It's exciting. It's not in our critical primary path, but it could be a valuable stepping stone as we look at basically different scale implementations of the technology to also fund the technology development.
Hi, Daniel. Great talk. I'm totally sold. But my question is, what are the bottlenecks outside funding? If you are given a blank check, how to accelerate the progress the fastest, and what are
Yeah, that's a very good question. So actually, we have, and I think it's clear for everybody. So we have, we are tracking some risks. We are working on the highest risks. We are removing them. I think, okay, I have not thought through what would I do with infinite amount of money. But I think I tell you what I would do with the money to accelerate the process. Most of our bottlenecks are ultimately basically just could be solved with money. So we basically need to build up buildings fast enough. So we are growing. We have outgrown our labs. So university was very nice, and we got a really nice clean room. But the big machine cannot go there. So it turns out that the power that the city of Tucson can provide is not stable enough and enough for these glass molding machines, so we need a bit more. So we are looking at whether to build our own building or move into another building, so that is a bit of a schedule driver. I think I don't see any really critical bottleneck. I see many gates that we have to pass through. But I think a lot of it is basically has to do with hiring people fast enough. So that's one of the challenges I have. Currently, we have more money than we can fill positions, so we basically are hiring. I think what I worry, but I do worry a lot about how to get the money, the infinite amount of money you mentioned. So I think the key point here is really the financial model. So there's a science layer of this, there's a technological layer, but none of that works if you don't have the finance layer sorted out. So this, I think why this is exciting is that this is a technology that benefits many communities. There are many, many groups that want to have cheaper telescopes that are deployed in larger numbers. So actually we have none of this funding is actually from NASA. We have other sponsors that are interested in seeing this technology happen, and they have science cases and use cases that are exciting at 0.5 meter, 1 meter, or 2 meter sizes. We don't have to reach 5 meter to be interesting. So that is basically our secret plan to get infinite amount of money.
All right, folks, we're at the top of the hour, and there's other questions, but I wanted to take the opportunity to thank again our speaker. If you have more questions, there's a secret plan for you. Daniel is going to be in the stats next, and so you can ask your questions there. And tomorrow, Daniel is going to be sharing in the Astro Coffee at 10 a.m. Bloomberg for 5th floor. You can catch him there too. His agenda is already pretty packed. But if you really want to nag him, just let me know. Tomorrow we're having some lunch at noon with some folks, so maybe you can join that too. All right, thank you so much, and enjoy the rest of the evening.
The cost models, which I don't believe in, but the cost models tell you and then you've got spacecraft, deployable, and all that stuff. So even if you reduce the cost of telescopes to zero, you haven't broken the cost of everything else. You have to do instrumentation and that deployable. That's non-refundable here. That's what SpaceX is showing. One of my biggest problems is comparing himself to the traditional way of doing things. He's assuming that regular projects like habitable will also take advantage of the launch costs. Right. Periscopes, mirrors, and replication. So, the saving you would have to how much the problem is just fair enough.
No, I mean the practical goes off.
Getting much. I need a different. I can't do this. I need a different. Yes, I need a grant. They email GHM and it never gets. And then they email again and again and again.